Well, I hope you all enjoyed lunch. Was it good? I hope you got enough. Our next speaker is actually quite well known. He was on People magazine, Kansas City Star. He was on Nightline, the first multimedia man, really. He actually appeared with his wife, Daphne, who we tried to get first, and we had to settle for the lesser known of the partners, Rich. Rich works at SPC along with Roger Edwards, so these are two forecasters this afternoon. And if you've ever read any of the discussions that come out of SPC, these two guys put out some of the best analysis, best understanding of what's going on in the atmosphere that we see from day to day. Rich is phenomenal at understanding, basically looking at sounding analysis, and that's what he's going to be talking about moisture return. He's going to be talking about how to look at upper air soundings and really understand what kind of environment that's going to set up for severe weather later in that day. And then he's going to take a little quick break and then do some talk on storm relative flow. And so with great pride, I introduce Rich Thompson.
I assume this is on. Everyone can hear me? All right, as Paul mentioned, I want to kind of take a two-pronged attack here. The first part of the talk, which is what was scheduled, I want to look at how we establish low static stability environments, essentially the elevated mix layer that Al Moeller, he showed a real good example in his sounding. I want to go back and take a look at how we establish the steep lapse rates in the mid-levels, and then also low-level moisture return. Essentially, before you can say anything about severe storm potential on a given day, you better have some idea what the history of your air parcels look like prior to that. So that'll be about the first 40 minutes or so. Hopefully I can wrap it up then. Take about a 5-minute break, and then I'll talk about some more recent stuff I've done with storm relative winds. Now I don't think this agrees exactly with the title Paul gave, but close enough. You get the picture. What I really want to look at is how we establish temperature and moisture profiles favorable for severe thunderstorms. All right, this comes straight from one of Chuck's numerous rants over the years. What do we need for thunderstorms? You can't talk about severe thunderstorms until you get a thunderstorm to begin with. So our basic ingredients, if you want to take an ingredients-based approach to this, is moisture, and most of the time we're talking about low-level moisture, essentially Gulf return flow, air mass modification. That's the primary process we look at. Instability. Now, Roger and I are probably guilty of this also from, say, SPC discussions. You often hear instability we're really talking about CAPE, but in this case we're talking about a more purist view, instability referring to static stability or temperature lapse rates is what we'll be talking about. And then, of course, there's lift. What I want to focus on is the moisture and instability. And of course, none of these matter if you're missing any one or more of the ingredients. All right. First of all, what are the basic sources for moisture and lapse rates in these cases? Well, I've done a little bit of work over the last few years on the air mass modification over the Gulf, and essentially, my first point, it's the evaporation of water vapor over a warm ocean surface, and that's essentially, usually the Gulf of Mexico gets the credit or blame for the moisture return. A lot of times, some of the maritime tropical return flows, dew points, say in the upper 60s or 70s, especially this time of year, is really air from the Eastern Pacific or even the Caribbean Sea. But that's a function of the water temperature. I'll get to that in a second. Later in the season, especially this part of the country, we have to deal with evapotranspiration when you have moist soil. Certain vegetation types, I guess cornfields are often blamed for these 80 dew points in Iowa. I'm not sure there's conclusive evidence to support that, but it certainly seems like a plausible explanation. And I'll show an example or two of that with some soundings. Now, there's also mid-level moisture. We don't just, in these parts of the country, elevated thunderstorms aren't necessarily as big a concern for severe storms, except maybe early in the season, say north of a warm front. But in the western U.S., most of the thunderstorms are elevated. So oftentimes you have to look at how can you get moisture to the mid-levels. And in this case, it's essentially horizontal or vertical advection, because how else, does anyone know of any way to get moisture in the mid-levels without bringing it from below? Anyone have any idea how you can do that? Well, I hear advection, but the whole idea is what's a moisture source in the mid-levels of the troposphere? Is there a moisture source? I think the point is no, it's all coming from the surface at some point somewhere. It may be in the mid-levels here, but that was a plume may have originated in the low level somewhere else. Okay, that'll be the first half of this discussion. And then the second half I want to look at the conditional instability, or basically how do we develop the classic loaded gun sounding profile, which is essentially related to surface-based heating and then vertical mixing in a boundary layer. And then it's a question of how do you displace a boundary layer from one place, maybe above the surface somewhere else, and that's the so-called elevated mix layer. And then, of course, of secondary importance, the adiabatic cooling. I'm really not going to focus on this. I believe Chuck's got an upcoming paper coming out. Chuck, is it weather and forecasting?
Well, don't hold your breath.
Okay, well, I guess it's in review. Some form of a manuscript dealing with this, but I believe preliminary indications, I'm not going to quote him on this, but is that the adiabatic cooling associated with vertical motion is probably a second order effect. We're primarily interested in establishing steep lapse rates with horizontal advection. So you occasionally, and it'll be me and my SPC colleagues, may refer to, lift and mid-level cold advection, cooling with vertical motion, destabilization. That is probably not a primary influence in destabilization in most cases. All right, how do moisture and instability vary typically in severe storm environments? Everybody's favorite one, the loaded gun profile. This is what tends to get all the press. Typical steep lapse rates overlying a very moist boundary layer. That sounding, I guess, was the opposite of a loaded gun. Okay, this is one that may be familiar to some of you. This is from the old Omaha sounding from just one of the tornado outbreaks back in mid-June of '92. And as you can see, in this case, the lifted partial trajectory is traced out by the dashed line. You can see it's a large positive area in the sounding, and primarily due to very steep lapse rates, low to mid-troposphere, and a very moist boundary layer. You notice these dew points are in the mid-20s centigrade, which is mid to upper 70 dew points. And of course, a shear profile that could also be interpreted as favorable for severe storms, but that's another problem altogether. This is the classic loaded gun profile. Okay, sorry about that. We've got other profiles that we have associated with severe weather over the years. The so-called inverted V, again out here, that's not very common, but in the western United States, most of the severe events are associated with so-called inverted V soundings. And what do we mean by this? Essentially, if you take a V and stand it on its end, you get this shape in the temperature and moisture profile. It's a very deep surface-based mixed layer, steep lapse rates, and relatively meager moisture profile. But in this case, you notice there is positive area on this sounding for a lifted parcel, and what you get is a profile very favorable for strong downdrafts with evaporative cooling, and you can sustain even a subsaturated downdraft below cloud base. So that's the so-called dry microburst sounding. Now this is one that, someone may throw something at me. My so-called Gulf Coast profile, I don't think this is officially recognized anywhere, but it's what's more typical as something that Roger and I face is looking at the whole country. We don't see loaded guns every day. We don't see inverted Vs every day. We see a lot of junk in between that may or may not be classified as anything. In this case, I show a sounding from the November '92 tornado outbreak. This happens to be Lake Charles, where you see some aspects of the loaded gun, but then in other regards, it's not. Notice there's no strong capping inversion. There's a hint of a stable layer well above the boundary layer, a much deeper low-level moisture field, and the static stability is generally not as low as in some of the loaded gun profiles. But nonetheless, this is a very common profile on the Gulf Coast, and this was in the middle of a very significant tornado outbreak. And finally, the so-called cold core, low-topped sounding profile that's almost always associated with marginally severe hails, the most typical occurrence. And here's one actually recently. This is from Little Rock. Almost a proximity sounding, I would say, not getting into all the problems associated with trying to classify it as such. There were Even though this sounding notes relatively meager positive area, we just get this very skinny cape. It's a fairly cold profile. You note these surface temperatures are in the 50s, but we did get quite a number of dime and nickel-sized hail reports with storms that were forming underneath the cold core low. Notice the vertical shear is relatively weak in the low levels in this case. All right, those are basic sounding types. Now the question is, how do you establish these and why are they prevalent in some areas and not so prevalent in others? And I guess Greg mentioned this, Al's mentioned this, Chuck's mentioned this. Storm types are related to the frequency of particular mesoscale environments. If the loaded gun profile is the most common in the plains, maybe that has something to do with why we tend to have higher visibility, more classic supercells, that sort of thing. It's only because the sources for low-level moisture and lapse rates are oriented such that we get that profile all the time. It's not to say that the cold core sounding doesn't occur in Oklahoma. It's not to say that the so-called Gulf Coast profile doesn't occur in Oklahoma or elsewhere. And that's something that if you're looking for source regions, you don't necessarily have to concern yourself with what climatology says it should be. You can look at what you actually expect it to be. Okay, return flow. This is one that a lot of people are real good at looking at models, and Roger's going to talk about this, saying, gee, well, the model's got this dew point, it's got that dew point. There'll be either will or won't be enough moisture for severe storms. Well, has anyone thought about how do you judge the quality of a moisture return forecast from a numerical model? What do you use? Anyone have any, favorite techniques they use for judging, gee, is this too much moisture, not enough? I mean, there's the obvious one. You look at observations. If their dew points are 10 degrees centigrade higher than the forecast at 6 hours into it, that might be a clue. But otherwise, say a day 2 forecast. Anybody have any idea how you would judge? Gee, is that moisture return into Texas, is that realistic? Can I expect 65 dew points on the Texas coast? I mean, any ideas?
Whatever the NGM is, double it.
Okay, the NGM times 2. That's one thing. Or I'm not necessarily going to advocate that approach, but if it works, I'm not going to argue with you. I know it's the NGM has certainly had that bias over the past number of years. Well, one thing that you notice, the Gulf of Mexico is quite a data void. I mean, if you look at the surface maps, you see there are a couple of buoys strung across the middle of the Gulf, occasional ships of opportunity, but generally not very consistent observations. But you do get temperatures and sea surface temperatures all the time out there. And occasionally at least the Western Gulf buoy has normally been reporting dew points, and there's a problem out there right now. But anyway, using that simple information and a simple conceptual model, you can actually estimate what type of dew points that a particular water temperature will support with a few simple assumptions here. And what I'm talking about in these assumptions is that if you look at the air sitting over the water, what should happen to the air temperature in the boundary layer over a water temperature of, say, 70 degrees? What should it look like if it sits there for a week? What should the air temperature look like? Say you start off with 50 degrees Fahrenheit. What's it going to look like after 2-3 weeks? Something that should be plenty of time for it to heat and moisten. I mean, any idea where's the temperature going to stop? Is my question. Is it
to the sea surface?
So it'll be close to the sea surface temperature. Now, this simple conceptual model is based on the idea that you can reach an equilibrium in the boundary layer between the underlying water surface and the air sitting on top of the ocean surface. And it's a balance between the latent heat flux from the water, the sensible heat flux from the water, and the radiational cooling of the boundary layer, and then mixing of dry air from above the boundary layer down into the boundary layer with subsidence flow typically associated with these high pressure ridges and offshore flow. If you let this process continue long enough, you will eventually reach some sort of equilibrium. Well, it turns out observation suggests it's pretty consistently around a 1 degree C or 2 Fahrenheit difference in the air sea, the water actually being 1 degree C warmer than the air, and then the relative humidity of the boundary layer is 80%. Now, the question is, why is the air cooler? I've actually kind of given the answer why, but why would the air be cooler than the ocean surface and not the same temperature? Well, radiative cooling, right. There's a radiative flux out of the boundary layer. You're constantly trying to balance that, but this is kind of a long-term equilibrium. You won't quite be in balance. There'll be a balanced state where the fluxes continue, but you won't necessarily reach the air temperature. So that's kind of a limiting case. Now, why is the relative humidity less than 100%? Why didn't it just saturate? Any ideas?
To reach saturation, the state of equilibrium.
Well, I'm already describing it as an equilibrium state. We're not saying that the fluxes have stopped, but why doesn't it saturate? And keep in mind this is large scale. We're not looking at just one isolated chunk of air. We're looking at a sort of a large scale equilibrium, what you would see on surface maps, that scale, not looking at tiny places in the boundary there. So I mean, any ideas? No, I don't think that would have anything to do with it. Because we're talking about over the water here.
Has something to do with if you evaporated any more water, the latent heat that it would take would reduce the air temperature down, and you're not at the saturation point.
Well, I guess one thing, if you're talking about essentially evaporational cooling, I don't think that's as big a role, because if you look at the heat capacity of water is about 1,000 times that of air. Essentially, any cooling, evaporational cooling over the water surface should try to cool the near surface air, but then it's constantly receiving more heat from below because the water temperature is not going to decrease just to, I mean, certainly not on the time scale of, evaporation for an hour. The water temperature, if it's 100 meters deep of 75 degree Fahrenheit water, that's a tremendous amount of heat reserve stored there. Well, essentially, it's pretty simple. If you look at we're talking about return flow, we're talking about essentially large surface high pressure ridges penetrating the Gulf of Mexico behind a cold front. If there's a high there, what does that say about the large scale synoptic flow? Is it characterized by rising or sinking motion in general in the lower troposphere? It should be subsident in the mean, because you're talking about maintaining a surface high. And we're also talking, what's typically going on, what's the sign of temperature advection? Is it cold or warm advection in most cases? Might kind of give it away. Essentially, front moves offshore. If it's a cold front, it should be low-level cold advection, which also contributes to subsidence. So what the subsidence is doing is it's bringing air from above the boundary there, and that's part of the whole idea, is to bring cold air down. We want to make a more stable profile on the large scale. But the key is that it's being constantly modified. So what you're doing is you're kind of fighting a battle between the addition of heat, which result in radiational cooling, which leaves the air temperature slightly below the water temperature. And this is assuming it's staying over the same water temperature for a long time. And then it doesn't saturate, because in the mean you're mixing drier air into the boundary layer due to subsidence. Okay, now I do have some other questions. We've already talked about why it's cooler. Is there any effect that you think the wind speed would have on this? And we're talking about a sustained wind speed, say for 24 to 48 hours. What would happen to the relative humidity, you think, if the wind speed in the boundary there were 10 meters per second versus 20 meters per second? Which one's going to have a higher boundary layer relative humidity if you let it stay like that? The 20. Well, it essentially enhances the evaporation over the water surface. So this equilibrium condition is a function of sea surface temperature and essentially wind speed in some secondary sense. Now, say you're looking at buoy obs, and you look at the Western Gulf buoy and you see an air temperature of 75, but the water temperature is 72. Does that tell you, would that be considered a significant observation? Would you think, oh, well, the buoy must be out to lunch, it can't be warmer than the water? Or does that tell you something significant? What would you think? Well, the more evaporation. Now you need to start thinking in terms of what's going on in the real world. Think in terms of a trajectory. And think in terms of what the I'll show you a Gulf SST analysis here in a second. But what's the distribution of water over the Gulf of Mexico, water temperature over the Gulf and the Caribbean? Is it the same temperature over the entire basin? Absolutely not. So this equilibrium state, for one thing, that gets hard to define. But fortunately, the gradient is largely meridional, where the temperatures along a particular latitude are somewhat constant. So if air is typically flowing out of the east for a long period of time, it may sit over roughly the same water temperatures. But how about it's a southeast or a south flow? Where's that air originating? What's the water temperature relative to, say, the Western Gulf buoy if the air is coming from the Western Caribbean Sea? It's warmer. Now that air may be in equilibrium. So if it's warmer, what that tells you is that air can't be coming from the area around the Western Gulf buoy. So in a sense, what I'm telling you is that this equilibrium state is kind of an ability to, as a parcel tracer, you can work your way backwards and figure out not only from the surface wind data, but from the equilibrium thermodynamic conditions, where that air must have come from. Because you can't generate dew points of 73 over a water temperature of 70. Essentially, that would be a supersaturated type setup, and it just won't happen. Okay, equilibrium thermodynamics. After grinding through this, you can come up with a simple conversion where you take the sea surface temperature, and I've done it conveniently since we still use the English units. This is the conversion for a particular SST will roughly support this dew point. So what you can do is you can relabel a Gulf SST map in terms of the dew points that the water will support, or the Caribbean Sea, whatever. And then it becomes a function of, gee, in my return flow, what's my residence time over a particular water temperature, and where's my air coming from? In this way, you can estimate what the dew point should be before you even think about looking at a model forecast. Okay, this is a color Gulf SST analysis. Generally the warmer colors, reds and oranges, are the warmer waters. Just for reference, this dark orange, these are temperatures approaching 80 degrees Fahrenheit, or about 27 centigrade. This is anyone know what this feature is called? This is just kind of a trivia thing, if anyone looks at the Gulf. Yeah, what I heard, I think I heard it. Somebody in the back mumbled it.
Loop current?
Yeah, the loop current. Essentially, in the mean, flow is coming out of the east, and you've got this gyre in the Gulf of Mexico. Any idea what this might be? Another trivia question. I mean, essentially, it's an eddy that occasionally, if you watch these consistently, some water, it's almost a gyre broken off of the loop current. Core of warm water that's drifted westward over a period of several weeks, and this was much more pronounced a few weeks before this. Okay, now the important thing I've done here is these annotated numbers here are dew points in Fahrenheit that the water temperature would support. So what I can do is I can say, look, if I think air is coming out of the Caribbean Sea, it reaches this equilibrium state, say it's been 2 or 3 days, undisturbed, easterly flow, and this air advects up toward the Texas coast, gee, if I was just starting right here, I might say, 65, that's the best I could possibly do. Whereas in fact, you might have 70 dew points. And as another important thing, this time of year, anytime you see 70 dew points, you can be almost certainly assured that it did not come from the Gulf of Mexico. Matter of fact, I think you could probably find that in South Texas. I haven't seen a surface map for a day or two, but that would be my guess. Okay, well, what do we do? How should you look at one of these return flow events? And I think the best way to do that is not for me to tell you something. Let's just look at one right now. This will be the April 19th, 96, the whole evolution up to the tornado outbreak in Illinois, Indiana. And I was one of the forecasters working through that series, and the return flow was a question in that case. Okay, we start off. This is essentially, notice I've gone back several days. And the important thing is I have to look at the prior history of the air before I can say anything about what I expect to happen down the road. We had typical mid-latitude shortwave trough, extratropical cyclone, front pushes into the Gulf of Mexico. Notice we have dew points I've analyzed. These were generally in the upper 60s over the Gulf Basin. And for that time of year, that's the Gulf or the Caribbean would support those dew points. Now, what does some soundings look like in the immediate offshore flow phase? This is Lake Charles, just prior to the frontal passage. And we have what looks kind of like the loaded gun profile. This was ahead of the previous cold front, fairly deep moist layer, steep lapse rates, which we'll talk about after the return flow is done. And there were indeed some severe storms, plenty of positive area with this sounding. Now, that's what we started with. So the important thing is if you look at this profile, you've got dew points near 20 or upper 60s, near 70 dew points. This is air that is likely near equilibrium with the water surface over the Gulf prior to the next return flow. So you know that you have maritime tropical air somewhere down there. Now, when the front comes through, we've noticed some pretty dramatic changes. There's been a lot of cooling. Of course, you see the backing winds in the lower troposphere with cold advection. And the boundary there's cooled quite a bit. You notice we were way over here on the previous sounding, and there's been quite a bit of drying. Otherwise, the profile hasn't changed dramatically. So it's mostly been in the low levels. And then here's what Lake Charles looks like. That was a morning sounding. This is even further into the event. Notice the temperatures have cooled. It's warmed in the daytime here, but above top of the boundary layer, it's continued to cool for some time. And notice it's quite dry. The mean dew points through the mixed layer are below freezing. All right, well, We continue on to the next morning. This series of shortwave troughs, several embedded in a larger scale trough in the eastern U.S., continue to move east. Weak surface ridge in the wake of this trough has pushed the front all the way across the Gulf of Mexico. Notice dew points are in the 30s and 40s, and at the buoys, air temperatures have cooled to the upper 60s, dew points in the 50s. So you can already see the effects. You can imply trajectories from the northeast here, short term. Notice the air is quite a bit warmer over the Gulf. So you're already seeing, and it's not nearly as dry, you've already seen the initial effects of air mass modification. And if you watch those, you'll never see it get nearly as cold out there because the path over water is several hundred miles before it reaches the buoy. Okay, this is essentially the tail end of the cold advection. We've cooled most of the boundary layer from being near 20 C down to 10 C, and then of course there's probably shallow radiation inversion in the morning. And notice it's quite dry through the lower troposphere. We continue on to that afternoon. Surface ridge has moved off to the east, and still these aren't particularly warm temperatures. Keep in mind it's April. You're still just in the upper 60s. You've got a mixed boundary layer. But dew points are still down in the single digits centigrade or in the 40s. But we do have the return of the veering profile, but notice it's weak. There has not been... What does anyone think the partial residence times over water have been? You know, like a trajectory. How long over water would you guess that air that was at Lake Charles had? What, 15 minutes? 3 days? Some guess. I mean, you need to have some idea if you're going to judge the quality of the return flow. What would you expect? If that was 3 days over water, I would think that we had a problem if the sounding looked like that. Turns out the flow was probably coming off southeast Louisiana and just following a loop back around into southwest Louisiana. And you can imply that from a time series of the surface maps. Well, we get to this time, next day. Let me get the date on there. This is the 17th. So we're 2 days before the tornado outbreak. And we're starting to get low 60 dew points come in. Notice the air temperatures have warmed, dew points have come up. And actually 70 over 64, if you calculate the relative humidity, that's not far from equilibrium for the water temperature here. But it's substantially below air-sea equilibrium for water that's more in the southern Gulf and the Caribbean Sea. And let's start to look at the soundings at this time. Lake Charles, this is the morning. At the same time, we start to see the boundary layer has moistened. Notice dew points were over here the night before. And it's still a relatively shallow boundary layer. But with time, you should expect this to increase. And we already have evidence over water that the moisture was indeed, or the air mass was continuing to modify. And here's Corpus further west. The return flow has been established a little longer, and we're getting a deeper mixed boundary layer and a little bit greater moisture values in an absolute sense. All right, now we're getting closer to crunch time. If we look at this, you see, okay, we're starting to establish a fairly broad moist axis. Dew points have now returned to the upper 60s. Again, you could rely on a numerical model forecast, or you could say, what were the dew points at the beginning of this whole episode? Does anyone remember what it was at Lake Charles prior to the frontal passage? It was about 20 C or 68 degrees. So essentially that was the low-level air mass ahead of the prior front. And these maps don't go far enough south, but that front died in the southern Gulf of Mexico. It never cleared the entire basin. So what's happened at this point is essentially air that was already at equilibrium is now coming back rapidly in the return flow. So some of this is modified continental polar air. Other stuff is air that's been maritime tropical for some time. And then just of larger interest, there are several potential weather makers upstream. And we go to Lake Charles. Now we've seen some fairly dramatic changes. And you notice I mentioned the maritime tropical air mass. Before that, mixed layer depth was about the same as you see here, up to about this level. Dew points are almost identical. So knowing the prior history, you could have anticipated that the dew points would return very nearly to the prefrontal conditions from 3 or 4 days prior to that. And we've got a much deeper moist layer, and then also we're doing some other things with westerly flow with bringing some steep lapse rates in. And we continue on northward since there wasn't much going on down the Gulf Coast. Lake Charles, we're also getting some moistening. These dew points are in the 60s now, and we're starting to look a little bit more like a loaded gun profile. And I believe that afternoon there was a tornado somewhere in central Illinois, if I'm not mistaken. It was a Decatur. There was something that was... Yeah, there were some severe storms with the initial... I mean, the moisture had not deepened as much as it would the next day. But we did have this this 1 weak trough, and there was a weak surface cyclone that went by, and you can see that's draped the front back down in Illinois. Now the question the morning of was, how far north can this moisture get? But you look down here, here's a good example. Look at the buoy, 73 over 73. What do you think that represents? Is that air that has a history over water at this latitude, or is it from somewhere south? It's obviously from south. Anytime you see something saturated, a dew point of 73, there's no way that water could support that physically. That's probably Caribbean air. And you can imply with trajectories come way down from the deep subtropical Atlantic. And also we've got surface boundaries around. We've got another upstream shortwave trough. It's not too hard to imagine some threat of severe storms this afternoon. And hopefully it's not hard for you to imagine that. And meanwhile, we look at Lake Charles. Dew points have now, except for the cool surface layer, they've increased to nearly the upper 60s. We're developing a fairly unstable profile. But we go north, and I think Lincoln that morning, that's not particularly impressive. But you saw Little Rock just upstream. You know that you've got a fairly substantial low-level moist layer poised to advance northward into Illinois later in the day. Well, what turned out in this case? What happened to it? Now, this sounding shows a lot of other processes going on. There were, if I'm not mistaken, near the time of the launch, there were supercells in the vicinity, a lot of convection around. But notice dew points have come up. The entire profile is moistened dramatically, which is very common. Just for reference, there's the morning profile. Notice, except for some evidence of probably high clouds, it's moistened dramatically in the lower levels. It's also warmed at the same time, and the wind speeds have all increased. So what you've done is simultaneously increase the vertical shear, and there's still the hint of the steep lapse rates, the instability, the shear, there were sources for lift, and the moisture, all simultaneously increased over Illinois during the day. And of course the model forecast suggested some of this, but again, if I recall, the dew points never got above, say, 64 or so in Illinois in ADA model forecasts, yet you had observations over a period of days that clearly suggested more like upper 60s should make it in there. And just since the second half I'll talk about hodographs, it's just kind of a precursor, a nice curved hodograph, and this is basically the observed storm motion. Substantial storm relative flow, because the storm motion lies well off the hodograph. Hence we had a fairly significant tornado outbreak. And then finally, this is just what it looked like when this whole thing pushed through the next day. Same sort of sequence, front pushes down. You can see on the NMC analysis several hints, or they've got several squall lines analyzed on here. And it's just a setup. Notice, what's important about this, that's a fairly weak pressure ridge behind the front, right? Where would you expect that front to go, say, over the next 12 to 24 hours? You expect it to surge southward in the western Gulf, or just kind of sit around in Texas? Also notice upstream, there seems to be on the large scale some sort of broad trough, and these short waves seem to be amplifying, reaching max amplitude somewhere over the plains. Well, does anybody know what happened just like 36 to 48 hours after this? It was the Fort Smith tornado. And that was actually a relatively widespread severe weather day all over eastern Oklahoma, North Texas, western Arkansas. And again, you were taking this air mass with 68 to 72 dew points that had been established at air-sea equilibrium and bringing it back. So in this case, you didn't even have to worry about air mass modification for that second return because you already had a source available. Well, what are some other things besides air-sea equilibrium that would be of concern? I couldn't let you guys get off without at least looking at this sounding a couple of times. You should remember the day. It's the Plainfield tornado day. This is the Peoria sounding near tornado time. Extreme CAPE in this profile. I mean, extraordinarily deep convective cloud layer. Now you notice these dew points though. I mean, that surface dew point's like 28 degrees centigrade. That's low 80s. And then, of course, even through the whole mixed boundary layer, you're still talking about mid to upper 70 dew points. Now, the question is, where do you get this stuff? I mean, if any of you, does anyone recall that case? I mean, looking at the series of surface maps, I'm sure somebody in here has looked at it in some detail. Could you trace that air back to the Gulf of Mexico? The 80 dew points. Well, I mean, I'll say here and now that you couldn't. Essentially, it's what some people might call, quote, pooling. I don't like that term, but it was a case where there was a blob of 80 plus dew points sitting over Illinois and Iowa. Well, where did it come from? Well, first it might help. Let's look at what the morning sounding in Peoria looked like. Sorry, I ran out of the fancy colored ones for this one. But this, you've got dew points that are respectable. This is a dew point probably in the low to mid 70s. You've still got the hint of the steep lapse rates. You've certainly got a profile that will support large CAPE values with afternoon heating and mixing. But notice these are not 80 dew points sitting down here. And winds are weak, so advection shouldn't be considered to be too exceptional in this case. Now here's the 0Z sounding with changes plotted on the sounding from 12Z. What I've done is I've shaded in green. That looks awful on this, but I apologize for that. That's anywhere that it's in green is where it increased from the morning sounding. And what I want to focus on is look what happened in the low levels. You've actually got quite a bit of moistening, and what could that be attributed to? Well, we had some southwest flow. You could argue there was moisture upstream that advected in. But what's another possibility? Right, evapotranspiration. This was during the afternoon. The soil moisture was high. It had been at least reasonably wet. This is the cornfields. It's late August. There's plenty of insulation. What happened is you're increasing the depth of the mixed layer with mixing during the day, and you're also adding moisture once the sun comes up due to the transpiration with the vegetation, evaporation of moist soil. And essentially you'll see that with these dew points. If you look carefully, like watch this summer, if we're moist enough up here, you probably will see the dew points in the 80s, mostly during the afternoon, and then they may drop off more in the mid to upper 70s by late night and early morning, and then they'll come back up again during the day. So essentially that's the idea that's what's going on, because you can't find dew points this high anywhere until you get to the buoys out over the Gulf of Mexico. And then unless someone's got some elaborate advection scheme that managed to avoid every observing site from Texas to Illinois for a week straight, it probably didn't come from the Gulf, not at least directly. And just for the heck of it, anyone wonders, this is using Chuck and Eric's virtual CAPE adjustment. That's a relatively healthy value. Anyone who's familiar, 8,572 for a surface. Yeah, I wouldn't be impressed if it wasn't over 8570, but you know. So anyway, the important things here are for this time of year. Air mass modification is critical for the return flow. Now, so you need to be looking at Gulf sea surface temperatures, and you need to be looking at for time continuity. Chuck mentioned this before. In the real world, you're not going to have just one map sitting here. I haven't been able to see anything else cut off from all data for months at a time. Maybe you do that to yourself, but chances are there's someone else did a map, there's data available. You can trace the history of this low-level air mass back several days, and you can have an idea 2 or 3 days in advance. Like, gee, today's Monday, Wednesday, am I likely to have maritime tropical air available for this next extratropical cyclone? And then of course the evapotranspiration is something more on a smaller scale that you would have to anticipate during the warm season. Would you expect that to be important this time of year? Would you expect the dew points to come up? And why is that? I mean, the ground, it's pretty wet out there to me right now. I stepped in the mud a couple of times. Moist soil, but what's the problem? It's cold. And I don't see much vegetation that would be contributing to transpiration, or maybe dead tree bark does something that I'm not aware of, but okay, that's only half of it. We talked about moisture, but we talked about this loaded gun. We need to look at static stability. And this is another simple one that people don't look at very often. They say, oh, well, it's a loaded gun. Well, how did you get that profile? Well, here's something. This is a paper from Lanici and Warner, Weather and Forecasting, 1991. There's a series. I'd recommend that everybody in here read these at some point. What this is an analysis you probably haven't seen before. These are surface potential temperatures. And for anyone who is unfamiliar with potential temperature, just can't remember, essentially we're talking about the temperature if you take a partial dry adiabatically down to the surface, or these dry adiabats. Those are theta values. And if you think about it with steep lapse rates, hey, that might be something nice to know. Well, this is essentially for the month of April, maximum surface-based theta values that show up. This is from climatology. And you notice New Mexico's got 36, maybe upper 30s, 38 C for the theta. Well, all that does is correspond to a moist, dry adiabat on the sounding. Well, let's look at a sounding from during the month of April at Albuquerque. First of all, one thing you'll note is that the elevation of Albuquerque is quite a bit higher than here. I mean, where are we here? We're around 1,000 millibars or just slightly above, whereas up there, they're above 850. Most of the Intermountain West and the plateau is somewhere between 850 and 700 for surface. So what you're doing is you're getting daytime heating, deep mixing, especially because it's a dry environment, and you create a steep lapse rate. Now you could actually say something, what's the importance of that? You say, well, gee, that looks kind of like the inverted V profile, but aside from that, big deal. Why do I care what it's doing in Albuquerque today when I'm interested in Dodge City tomorrow? Well, where are you going to get, how do the lapse rates get to Dodge City up in this layer? Do you think that Dodge City typically heats and mixes from the surface to 500 millibars? I mean, does anyone think that's typical? And notice Dodge City's elevation is quite a bit lower. We're down more like 900 millibars. So how could you get a steep lapse rate above the surface over Dodge City? Advection, right. It's pretty simple. I mean, you're essentially talking about surface heating. So if you have sunshine over elevated terrain to their west, we can actually overlay Albuquerque. Well, look at that. There's hardly any difference above the boundary layer in those two profiles. And the reason is you trace the air back from Dodge City through the low to mid-levels. Lo and behold, it came from the southwest more than likely, and that's essentially yesterday's surface-based mix layer. Has moved out over the plains, but more importantly, out here in the low levels, you may have trajectories that originate from somewhere else. And with time in this Dodge City example, we continued with the elevated mix layer, which forms the so-called lid or capping inversion. And then also from the low levels, the flow was from the south and southeast. We brought in low-level moisture from the Gulf of Mexico. And what we've done is we've gone from what was initially a dry-sounding, not terribly unstable, to a loaded gun type profile. And actually this was, this event, at least Dodge City, did precede a fairly significant severe event back in mid-April of 1991. Greg showed some pictures of a tornado from Oklahoma later that same day. Well, what happens as the season progresses, we move into May, what would you expect to happen to surface theta out over the high terrain? It should increase. Sun elevation angles increasing. And notice these values went from 36 to 40, now they're 40 to as high as 44 or greater centigrade. And again, we take another case associated with severe storms later on. Again, it's a notice at Albuquerque, surface-based mix layer. And then we continue somewhere east of there. Here's Amarillo. Well, in the low levels, the flow is out of the southeast, so it's not bringing in air that was anywhere near Albuquerque, but up above the surface, this more west-southwest flow is that mixed layer. And as you might guess, you can overlay these two, and that layer right there in the middle, very nearly identical temperature profile. So essentially you're transporting air from the elevated heat source over the lower plains area. And again, same sort of thing, Dodge City, that's how you get this loaded gun type profile. Moisture from the south in the low levels, dry air and steep lapse rates from the west. And of course, this is snapshot doesn't necessarily do justice to this case. The flow was westerly or southwest before this. And then finally we move on to June. And this is when values continue to increase. These are 48 or greater, and here 48 to 52C. So what happens is, as the season progresses, the mean temperature of that mix layer will increase. But fortunately for everyone who likes storms, so do the low-level temperatures increase, and typically water temperatures and dew points they support also increase simultaneously. Just another example. Notice the structure of these soundings is all remarkably similar. These are from April, May, June, different years, different events. Again, a nice surface-based mix layer. There's actually your surface-based contact layer where it's super adiabatic. And again, you can track that air back. Dodge City, here's another one of these profiles with very steep lapse rates and the beginnings of some low-level moistening. Now, what does this all look like plotted all on one? I just sketched out the mix layers from the three cases from the 3 different years, and you notice the depth of the mix layer doesn't really change that much over the high terrain, and all that happens is you're pushing it to the right. So it's a question of, gee, if I go back and use an analysis like this, say it's going to be sunny, it's a June event, what type of mixed layer temperature should I expect? What type of how strong will my cap be? You can simply use something like this to estimate what the theta value would be. In other words, which dry adiabat will the profile likely resemble? And then when I vec this out, it's just a matter of looking at what level I'm talking about to determine, is that too warm such that it inhibits deep convection, or is it just right with some loaded gun profile? Now, I have mentioned advection several times. This is borrowed from Chuck's paper that's in review. This is looking at August, and this again kind of ties into the playing field case. You notice on that one there were also very steep lapse rates involved. Not only the incredible low level moisture, but steep lapse rates. Well, if you look up here in the mid-levels, these are various layers, like low levels. This is 700 to 500 millibar layer. And what Chuck and John Cortinas have done is calculated a measure of static stability, which is proportional to the lapse rate in the layer. And the lower values approaching 0 would be dry adiabatic, would be a value of 0. So this is a mean in the evening. And you notice there is even a hint in this flow. You see this dotted contour? That's kind of the mean geostrophic, some sort of height through that layer. So it implies in the mean there's sort of a weak ridge in the west and west-northwest flow. Notice how the lapse rate static stability seems to elongate in the direction of that geostrophic flow. So what it's saying is that there's a tendency along the direction of the mean wind to have these lapse rates advect out over the lower terrain. And you notice the further you get removed from the high terrain, the greater the static stability is, at least in the mid-troposphere. So what this is saying, pretty straightforward manner, is if you want steep lapse rates, if you want a loaded gun profile, you've got to look upstream in the low levels for moisture and upstream in the mid levels for lapse rates. Things you might wonder about, it's like, gee, if it's only a day after a frontal passage, the low level air may not have modified enough. If it's been rainy or cloudy over the Intermountain West, would you expect that deep mixed layer to show up? No, it's probably, the key here is you want sunshine out there so you can establish the deep surface-based mixed layer. But the simple thing there, and it's remarkable how few people actually look at it, all they have to do is, gee, I've got low-level moisture sitting here in Texas, I've got steep lapse rates sitting over the southern Rockies. It's not too much of a reach to see that ending up with southwest mid-level flow, low-level southerly flow, ending up with a loaded gun profile over Kansas, Oklahoma the next day. And you can actually say something about the magnitude of the moisture and of the mixed layer. All right, I'll go through real quickly, just sounding a transition in this case. This was just how the profile changed at St. Cloud in one of these cases. You start off with sounding that would probably be supportive of thunderstorms anyway, deep moist layer, but not particularly steep lapse rates to begin with. And what this will illustrate is the elevated mixed layer spreading over Minneapolis from the west. And you remember in the other example where the air tended to be coming from this time of year. Notice I'm looking at an August case. So you notice that in the mean, it's kind of elongated across the northern part of the Central Plains at least. Okay, the next sounding in the sequence still, there's maybe a hint of some steeper lapse rates in here. Notice the flow is getting a little more westerly, but it's still very moist. That's not typical of the deep mixed layer. Now what's happened? Notice really the only thing that's changed in this sounding, the flow veered to westerly. But what happened? This brought steep lapse rates from somewhere west. Now you could look at soundings upstream from the day before and say, oh, well, look at that. You know, I'm looking at Rapid City, and I've got a very deep elevated mixed layer sitting out there. All I've got to do is, if I change the flow regime, I can move that stuff over the low-level moist axis further east. And then with time, what we've done is, voila, this is a series, these were all 12 hours apart. We've gone from a very moist sounding that was oriented right here to a classic loaded gun and a cape just under 4,600 joules per kilogram. And again, a wind profile that may or may not be supportive of severe storms. Okay, real quickly, we try to look at this stuff with some of the numerical models, and also aside from the observations, I trust the model to do a better job of moving these air masses around than my first guess is just glancing at some surface map. And we can plot temperature differences. In this case, the shaded area is 850 to 500 delta T's, or essentially converted to lapse rate. These are in degrees C per kilometer, and if you remember your profiles, conditionally unstable lapse rate starts at about 6.5 degrees C per kilometer. for these temperature ranges. So what this shows is an area with a cold air in the mid-levels, but there's also steep lapse rates. Whereas down here, this is probably due to heating over the mountains in Mexico. All right, if you take anything from this part of the talk, pretty straightforward. If you're looking at moisture return, look at low-level trajectories. I know most people don't look at that. Unfortunately, nobody seems to want to put it on any model forecasts either, which could be very valuable, looking at where the air came from in the first place. And then what's the sea surface temperature? And you can get a good idea, what kind of dew points should I expect? Mid-level lapse rates, pretty straightforward. If there's elevated terrain to the west of you most of the time, like the Rockies, we've got a perpetual source for steep lapse rates. It's just a matter of moving that air eastward and getting it in conjunction with some low-level moisture. And then also, which should be obvious by now, if you're going to look at destabilization, which in itself implies changes in the profile, you can't look at snapshot values. Like, oh, well, here's what it looks like at 12Z right here at Lincoln. I think that looks great for severe storms. You better look upstream to have some idea how that might change. So that's all I've got on the first part. I don't know if there are any other questions. I can take those now. If not, I'd like to take maybe a 5-minute stretch break, and then we'll completely switch gears, and I'll talk about some storm relative flow and tornadic and non-tornadic supercells. So, yeah.
I see that Nesbitt has hourly gauge soundings now. You know, are those of any value?
Those ghost soundings, first of all, it's very difficult to verify the soundings, obviously, because we don't have any balloon launches over the water. They may be of limited value. I think you can almost imply what the boundary layer looks like better looking at the underlying sea surface temperatures than you can from looking at that sounder information, because that's going to smear things out vertically, is my impression. Yeah?
You mentioned the role of vertical velocity in changing your lapse rate.
Well, essentially, I guess I did way at the beginning, the adiabatic cooling, essentially vertical stretching, or if your profile is unsaturated and you lift a layer, it will cool. And you'll tend toward a dry adiabatic profile. But I think that in most cases, that's a second order effect for most central and eastern U.S. severe storm event. Did I make it? I was close to 40. Be quite a change from the first part. Oh, certainly. Okay, here for the next, say, 35 or 40 minutes, I want to try to present some results of some work I started probably back in late 94 and continued through 95 and 96. This is essentially based on a conceptual model developed by Harold Brooks and Chuck Goswell, Wilhelmsen, and Davies Jones in the 93-94 time frame. I would suggest you read a series of papers in Weather and Forecasting and the Tornado monograph to get some background information on this. But what I was interested in doing was trying to discriminate between tornadic and non-tornadic storms, and I'm going to be politically incorrect, and I will discriminate, so I apologize if I offend anyone in the audience. So, all right. If we're looking at supercells, we've been talking about thermodynamic profiles a little bit, but there's been mostly cursory mention of shear parameters for supercell storms. Well, what do we use operationally to forecast supercells? Well, there essentially have been kind of two camps for the last 5 to 10 years. There are those who only want to look at storm relative felicity, and then there's probably a smaller group, much smaller group, that only want to look at the Bulk-Richardson shear term or parameters related to that. Now the question here is, we've got rough guideline values for each of these. The Bulk-Richardson shear, which may be a little less familiar to you guys, is just the shear term from the Bulk-Richardson number. And this U average is what's important. It's just it's essentially a shear vector between the deep layer mean winds and the low level winds, and typically defined over the lowest 6 kilometers. And looking at values in the range of 40 to 100 meters square per second square, those are typically associated with supercell storms. A much simpler way to do this, which seems to work just as well, if not better, is just looking at the surface to 500 millibar shear vector, which covers about the same depth. Values of 35 to 40 knot shears tend to be the low end when you start expecting supercell structures. Now there's the storm relative helicity camp, which is much bigger. Typically you've seen, this goes all the way back to, I guess, the Sphere Storms Conference in '90, with a relatively limited sample suggested rough lower threshold. I use that in quotes because there is no magic number, but talking about 150 meters square per second square for supercells. Now, what are the advantages and disadvantages of each approach? Obviously, the BRN shear, there's one thing that it has a big advantage over storm relative helicity is that you don't care about storm motion. You can use the BRN shear to forecast a shear profile favorable for supercells without having to make any assumptions about storm motion. Whereas using storm relative helicity to forecast the supercell is kind of like admitting that you're going to have supercells in the first place. So that there's something a little tricky there. If you're going to assume you're going to have a supercell, why are you even using it to forecast? You've already kind of answered your own question there. Well, in recent years, with all the emphasis on improved warnings and with all the 88D installations across the country, we're starting to find out that not every rotating storm produces tornadoes. I guess the background information here was back in the 70s and early 80s, the Doppler radars were run in Oklahoma, and I guess Don Burgess was associated with some research that suggested half of all mesocyclones are associated with tornadoes. Well, essentially, they had the one major problem with that study was what days were they collecting data? The days they expected supercells and tornadoes. They didn't have the radar running all the time. It was in research mode. So they took a bunch of high-end Oklahoma tornadic cases, and sure enough, probably on those days, it's about 50-50. Unfortunately, when you run the radar 24 hours a day, 365 days a year, you see a heck of a lot more rotating storms that don't produce tornadoes. And the question is, can you discriminate between these environments? Because if you just say mid-level meso equals tornado, then your false alarm's ridiculously high. And there's a lot of people right now that are struggling with this. Okay, so what are some parameters we've tried to use recently to discriminate these environments? I guess the CAPE and storm relative helicity have been used, and this was John Davies and Bob Johns and John Davies have put together probably some graphs that most of you have seen with the distribution of CAPE and storm relative helicity. It's some curve, looks like this, and then everything to the upper right is where most of the supercells and then occur, and the further you go up toward the right with increasing CAPE and increasing storm relative helicity, you tend to have more tornadic storms. But there's a whole heck of a lot of non-tornadic storms. In looking at it operationally, it seems to do a real good job in discriminating supercell and non-supercell environments, but it doesn't necessarily tell you for sure that there will be tornadoes with the supercells. There have also been attempts, this is much more recent, you can look at the last March's, or actually last September's weather and forecasting with the Bulk-Richardson shear term, not the Bulk-Richardson number, combining that with some low thresholds of CAPE and trying to forecast areas where the shear and CAPE suggest tornadic supercells. And they met some reasonably successful forecasts there, but the fields are extremely messy and difficult to interpret using the mesoscale model. Okay, well, I've already talked about some of these problems. Now, the one with the EHI, the Energy Helicity Index, is you can get a very large looping hodograph, but occasionally the storm motion falls very close to that hodograph. And that says that the storm relative flow near the level of the storm motion, or whatever level that is relatively weak. So you can get very large helicity values, large CAPE values, and hence a large EHI. But I will show some cases where that just may be a failure mode for tornado genesis in general. Okay, then there's the BRN shear has been used kind of as a surrogate to storm relative flow because people say, well, gosh, I don't want to, if I'm not going to use helicity because I have to assume a storm motion, why should I use the storm relative flow? Because I've got to make the same sort of assumptions. And that's a valid point. Now the question is, does the BRN shear in itself say much about storm relative flow? Again, I'll show some data that suggests that there's not a very strong relationship between the two. The contention was that BRN shear increases, so does the storm relative flow in the mid-levels, and it's not quite that straightforward. So what I decided to do is say, what the heck? I mean, if people have been looking at stuff where they're already assuming a storm motion for the helicity computations, why not just go ahead and use the assumed storm motion and get at the problem at hand, which is the storm relative flow through the depth of the troposphere. So I took that conceptual model, which I'll show now from Chuck and Harold and others, and decided to calculate or just collect a whole bunch of cases. Okay, this is a very simplified version of the conceptual model. Now, one thing I want to say right now, Al just presented all the stuff with supercells. There's the argument of, is there a continuous spectrum or storms clumped into groups? Don't take this classic LP, HP stuff and these so-called echo configurations too literally. What I should probably call these are outflow-dominated supercells. I don't care exactly what the reflectivity structure looks like, because you can be virtually guaranteed that the low-level outflow structure of 10 storms that look like this is dramatically different for reasons I'll get into shortly, or at least a few of the reasons possibly. But in some basic sense, the conceptual model is pretty straightforward. And Al's talked about this, the rain distribution in a storm. If you have very strong winds in the mid and high troposphere in a storm relative sense, then where's all the rainfall going to end up with respect to the updraft? I mean, it's going to end up downwind from the updraft typically. Does that leave a lot of rain for a mesocyclone, assuming that it's a supercell storm, to wrap around the backside of the storm? Say for a hook echo, would you expect a narrow hook echo, no hook echo, big hook echo? I mean, does it make sense that if all the precipitation is removed, it's very difficult for the storm to wrap a lot of rain around the backside? So the idea here is that in these cases, instead of an LP supercell, this one maybe Eric would like, it'd be more like an outflow challenged supercell. Because in this case, all the precip is well removed down the forward flank of the storm. The mesocyclone may even trail most of the precipitation, and there's not much in the way of cold outflow on the rear flank of the storm. Now, in Eric's talk, he'll present some ideas for tornado genesis. Chuck and Harold have some different ideas that my work actually follows more closely, but I don't think it's terribly critical exactly how the RFD can help lead to tornado genesis. The important thing is that you have an RFD that does not undercut the storm, and I think that the idea of the storm relative winds in the mid-levels can help you anticipate when it's likely to be out of control and undercut the storm, which is this case, when it's likely to be some sort of balance, which is the so-called classic supercell, or when there's liable to not be enough of a rear flank downdraft to get anything going in the first place. So what I mean by balance, I've drawn some wind barbs on here that don't take this too literally. I don't mean the strength of the outflow has to be exactly that of the inflow. But it's the idea that this structure of these gust fronts, the forward flank, as Al called it, pseudo-warm front, and the rear flank gust front, stay fairly consistent with respect to storm structure. Of course, you may have occlusions and tornadoes and minor variations, but in the long haul, it keeps the same sort of configuration. This gust front does not surge out ahead of the mid-level mesocyclone very far, or at least not for long periods of time. In this case, these gust fronts, I couldn't get it to work on my software, but they should be kind of dashed. They're very weak, or maybe not, you can't even find them at the surface. Now, the failure mode that I'm most interested in is this case where you wrap a lot of rain around the rear flank of the storm, there's a lot of cold outflow generated, and the outflow undercuts the mid-level mesocyclone very early in the life cycle of the storm. In that case, it's difficult to couple any developing low-level mesocyclone with the mid-level rotation and get a strong, persistent tornado or continually repeating series of tornado events. Now, this does not say that there can't be tornadoes with HP storms, because that's not at all true. Typically, they're early in the life cycle, or even as Al showed, some stuff that looks like it may or may not even be supercell processes going on. Stuff on the gust front north of an apex of a bowing structure that this could evolve into. There's a myriad of possibilities, but the important thing is that you don't tend to have strong and long-lived multiple tornadoes with those kind of storms, typically. Okay, so what did I do then? I said, oh, I got to attack this problem somehow. I said, I'm going to just go grab a bunch of supercell cases. I look at the whole country all the time. I've got access to radar data. I can grab as many of these things I want. I can get the radar-derived storm motions of the echocentroids over a period of about an hour. And my next question was like, well, gee, okay, I want to do the storm relative winds. What do? Do I use proximity soundings or something else? Well, again, Chuck's got some stuff out there with some interesting discussions about problems associated with proximity soundings. How do you choose a proximity sounding? And Eric, I don't know if you have any examples, any of those things to show the variability on the scale of like 50 kilometers around a storm, some of these vortex storms, but it's bewildering that you can get soundings that look totally different just 50, 100 miles apart. So the question becomes, what the heck is the environment of the storm? So I said, well, I don't want to sit around and wait whatever the estimated 25 years it would be before enough storms happen to move 5 miles northwest of the sounding site at 0Z to get a bunch of cases. So I said, well, you know, there is one thing that I can use. I said, in the numerical models, we do have the initial panel, which is, in a rough sense, it's an analysis of the observed data. It doesn't exactly fit the observations because it's got to be in agreement with the physics of the numerical model so that the thing doesn't blow up on you. But in some rough sense, it should be at least a consistent process. They apply the same sort of constraints to the data day in and day out. And the important thing is over a large number of cases, hopefully there'd be some kind of signal would emerge. So what I did was I said, well, I had PC Grid's data for those of you in the Weather Service who are familiar with it. And at the time was limited to mandatory pressure levels. I just said I'm going to calculate the storm relative wind speeds at the mandatory pressure levels that most closely approximate the low-level inflow layer, the quote mid-levels of the storm, and then I even decided to look up at the top of the storm just out of curiosity. And I did this because I'll have an initial analysis from the model field every 12 hours, regardless of whether a thunderstorm hit a RAOB site and contaminated a sounding. All that sort of stuff should be removed from the model initialization to a large extent because that's not what the model's trying to forecast. It's on, as Chuck said, the sounding may be totally unrepresentative of the larger scale background environment. And that's what I'm interested in. Is there a larger scale background signal here? So what I'm doing is saying, is there anything I can pick out of these coarse model fields that can tell me anything about whether the most intense storms will be tornadic or non-tornadic? Okay, after doing that, I collect all these cases and I try to come up with a forecast scheme that in real time could give you some estimate of the tornado potential with supercells. Now, it's important to note my definition of significant here. I called a supercell tornadic if it produced long-lived, and by long-lived I mean at least one tornado that lasted 15 minutes or more, or multiple tornadoes. They could be brief, weak, but they had to occur at least over a 30-minute time period. So what I'm implying here is that Chuck and Harold's conceptual model doesn't necessarily say anything directly about tornado genesis, but this idea of the rainfall distribution can be related to the likelihood of a sustained low-level mesocyclone. So what I'm saying is if there's a sustained low-level mesocyclone, it's perhaps more likely to get tornadoes with those kind of storms than storms where the low-level mesocyclone is either brief or displaced in the vertical a substantial distance from the mid-level mesocyclone. So keep in mind, what I'm calling non-tornadic from here out can include single brief weak tornadoes. I didn't have any brief strong tornadoes, but I did have several storms that produced descriptions in storm data such as short narrow track, brief touchdown in a field, no damage, that sort of thing can occur. But I'm calling that non-tornadic because this conceptual model doesn't preclude tornado genesis early in the life cycle. What I'm interested in is longevity of the tornado threat. Well, here's the cases I came up with, meeting all the criteria. Had to be within 3 hours of the synoptic analysis time, 0 and 12Z. Solid squares are tornadic supercells, and the X's are non-tornadic supercells. I tried to make sure it was a diverse database so that we wouldn't have any of these people that say my storms here are different than your storms there. This is just wherever the heck they showed up. Now, it just so happens that, no big surprise, more of the supercells were in the plains than anywhere else. Some of this may be a function of the time of the sounding releases being at 0Z. That's a pretty common time for deep convection out in the plains, whereas a lot of times storms have already dissipated in the eastern U.S. by then. So I did miss some storms in the east that occurred before my 3-hour window, and a lot of high plain storms and stuff in the west maybe hadn't occurred yet. So this is not necessarily the best way to do things, but I didn't have a lot of choices. Okay, let's follow that whole line of reasoning. What did I come up with all these cases? Well, I'm going to show the stuff that I think worked the best first, and we'll take it from there. This is a plot of each tornadic and non-tornadic supercell, same convention with the tornadic ones and the heavy squares. The storm relative wind speeds based on the observed storm motion at the grid point, closest grid point, in the ADA analysis to the observed location of the supercell. near 0Z, within the 3-hour time window I put there. And you do notice that as we go across the x-axis here, these are the surface or boundary layer storm relative winds. The vast majority of all the supercells don't show up until you get, say, 8 meters per second or so, and they're all to the right of that, and typically around 25 meters per second. I just didn't have any cases above that. Now, on the storm scale, that probably varies quite a bit. I mean, anyone in here that's chased knows that the near storm environment can be substantially different than this background stuff. But it does show a tendency for sort of a lower bound. But notice the non-tornadic and tornadic are all over the place over that same range of values. I don't see anything if you pick any particular value on the x-axis, and it doesn't seem to discriminate at all between tornadic and non-tornadic. And what this can tell you is that in some ways it tells you why storm relative helicity might not, because large helicity values should be correlated to strong storm inflow in some sense. Now, I'm just looking at the surface, so that's not necessarily true, but what it says is that you could, in some sense, you could replace this with storm relative helicity, and you probably see the same sort of thing, where large helicity doesn't necessarily guarantee that it's going to be a tornadic storm. It just says that a certain degree of storm inflow is important, but beyond that, it doesn't tell you anything about the tornado threat. Now, look on the y-axis at the mid-level, my version of the mid-level storm relative flow. Look around 8 meters per second. Notice all the tornadic storms, I think the weakest one is like 7.9 something meters per second. But generally around 8 meters per second, or about 15 knots for storm relative flow. All the tornadic cases are above that. There's a lot of non-tornadic cases mixed in there. But notice there is also a substantial part of the population falls below that. And they continue all the way down to some really pathetic values. I mean, 3-4 knots, something like that, where the storm motion falls real close to the photograph at 500 millibars. So there does appear to be some signal here. It doesn't look like it explains everything, but what I could call this is, and this is 131 cases, just if anyone's curious. It looks like we might have what Chuck referred to as one of the more typical, maybe a necessary but not sufficient condition for sustained tornadic supercells. Just because you're up in this region of storm relative mid-level flow doesn't guarantee you're going to be tornadic, but it seems like if you're down below that, it's a pretty good bet that you won't produce significant or long-lived tornadoes. Now, I looked at some other parameters just for comparison. Here's the Bulk-Richardson shear term compared to the 500 storm relative mid-level flow. There's a clustering supercell. These values get awfully weak. That's a lot lower than the threshold of 40, which I showed you on one of the early slides. Part of this is probably an artifact of my course resolution and the calculations for PC grids. But it does seem like that most of the values, once you get around 20 or so, it's greater than that. But that's a relatively low shear value. If you looked at observed soundings, you see that all the time. That would rule out virtually nothing, except for cases where there's no flow. And notice going across here, there's quite a bit of the overlap, again, between these two. Almost to the lower bounds and upper bounds of both tornadic and non-tornadic cases, they're all intermingled. There's maybe a little tendency for more tornadic over here and more non-tornadic down here, but it's mainly on the low end of the shear. And you remember earlier my contention was that the storm relative mid-level flow is not necessarily implied too well by the Bulk-Richardson shear. If you look at the tornadic storms, if you put a best fit through here, if this were a one-to-one relationship, you'd certainly expect them to increase something like this. The point should be oriented whereas the Bulk-Richardson shear increases, storm relative mid-level wind should increase, whereas they go up this way. However, my best fit line has a linear correlation of only 0.3. So what it says is that there's something about the storm motion that is keeping the storm relative mid-level flow much more constant than using the assumption that it increases with BR and shear would suggest. So that's what I use as also supporting evidence for looking directly at the storm relative mid-level winds instead of trying to imply it with another parameter that doesn't seem to work too well. It's not a very strong relationship. If you use all the cases, even down here in the low end where it looks a little bit better, it's still only a correlation coefficient of 0.44, which is not very good. Okay, finally, my high-level stuff. Again, this looks a lot like the low-level storm relative flow comparison. There seems to be a lower bound to the supercells in general, and they expands a wide range of values from about roughly 20 knots or 15 to 20 knots all the way up to 70 knots if you convert these values. but tornadic and non-tornadic are all over the place, whereas if you look on the vertical axis, more of the non-tornadic seem to fall out of the pile looking at the mid-levels as opposed to the low and the high levels of the storm. Well, I can summarize these statistics. Here are some of the mean values and standard deviations. The surface storm inflow for the tornadic and non-tornadic, I mean, they're within a half a meter per second on the mean. Standard deviations around 4 just suggests that there's a lot of overlap between these two. It's quite a bit of variability in these values from storm to storm and a lot of overlap. Look at the high levels. Tornadic storms tend to be a little bit stronger than the non-tornadic. Again, wide range of values with a standard deviation of 8 meters per second. So there's a lot of spread in the data. Now if you go to the mid-levels, you get fairly significant values around 26 knots, 27 knots or so. But then you look down at the non-tornadic, and it's about 4 to 4.5 meters per second weaker, which is almost the magnitude of the standard deviation. Now, since it's not much bigger than the standard deviation, that suggests there's still a lot of overlap, but this difference in the means is statistically significant, and it's certainly more pronounced than the other areas. Another way to break this down is looking at some categories. Threshold values of storm relative wind speed. You notice for the surface, you get similar distributions for the tornadic and non-tornadic cases. Almost all the values fall between 10 and 25 meters per second, roughly the same fraction in each of these categories. And you look at the high levels, same sort of thing. It's a little more spread out on the non-tornadic storms, but still same sort of distribution. Now meanwhile, look at 500. 81% of these are in the range from 10 to 25 meters per second, or what I'll call 20 to 50 knot mid-level storm relative flow, whereas 60% of the non-tornadic storms were less than 20 knots. So that's at least a fairly pronounced difference. Well, I did come up with a forecast technique for this stuff, and I thought, well, let's try it on some high-end cases. If it doesn't work there, then I might as well quit now and save myself the trouble. This is back from '95. One of the cases, this isn't totally independent, but it was a case that was used in determining, it's in the scatter plot. But what I did was I went back in a forecast mode. We wrote a macro and PC grids to calculate the storm relative winds. We're assuming a 30 degree, 75% right moving storm of the mean wind in the lowest 500 millibars. Again, that's a weakness of this technique that I will harp on a little bit later. You have to be careful, make sure that storm motion makes sense before the technique will work. But what I did is the shaded area is everywhere that for the 12 and the 24-hour forecast prior to the event, the storm relative winds were greater than 15 knots. I looked at all the plots, and all of them suggested around 8 meters per second for a lower bound. So I used that as a lower bound on the low level, in the heavy lines, and the mid-level storm relative wind in the dash lines, and the overlap of those two where there was at least a cape of 500 just for reference. So you would at least expect deep convection. This whole area shaded is where the so-called storm relative wind was favorable for sustained tornadic supercells according to this conceptual model. Now what I've done is I plotted the location of one of the storms near 0Z that had produced a series of violent tornadoes in northern Alabama. This day is May 18th of '95. It didn't get a lot of recognition, but there were, I believe, 95 tornado reports that day. It was over a pretty broad area all through here, and then there was another cluster of tornadic storms near Chesapeake Bay. But again, I said, okay, fine. It took a high-end case and it worked reasonably well. Well, here's one that you may see a little bit of stuff from later. This is June 8th of '95. This is the forecast from the ADA model from that morning. And I just plotted rough locations of the Allison Kellerville supercell and then the Chuck's Pampa supercell on here. And they're well within the area of overlap in the storm relative winds with plenty of CAPE in the model forecasts. Again, that was not a particularly difficult forecast to anticipate some threat of tornadoes. Well, how does this do in more marginal cases, which obviously are some concern? This is July of '95 up near Minneapolis. There was a cluster of supercells produced several F1, F2 type tornadoes. None of them particularly long-lived, but there were a whole bunch of tornadoes. And this is the location of the supercell. And indeed, if you look at these absolute values, they're weaker than the cases I just showed you, but there still is overlap in these rough 15 to 20 knot values of low to mid-level storm relative flow. So it suggests if storms do form in this area somewhere, there certainly is some potential for a sustained tornado threat. And of course, you know, a lot of this depends on exactly how right the model is. I wouldn't put a lot of faith in, gee, I'll go here if I'm a chaser, but I'm not going to chase there or there. You can do that, but I think we all know what's going to happen to you in the long run. Okay, here's another case that was kind of late season, late July of 95, where there were supercells on an outflow boundary, which may have also been important. And actually, it's especially important for this graph, because if you look at the dashed lines, the forecast of storm relative mid-level flow, 15 knots, 20 knots, generally it increases over the Texas Panhandle. And these are moderately strong values, 20 to 30 knots. The limiting factor in this case, from a forecast standpoint, seemed to be the low-level inflow. This is 15 to 20 knots in this egg-shaped area. Now, there was one tornadic storm on the Red River that did fall within this area, but this one in Amarillo's, that's a little far away to say, oh, close enough. I don't think that in and close to the watch area stuff would work for this. That's probably removed 150 miles or so. And the question there is, if you're looking just at the numerical model, should you expect the ADA model in a 12 or 24-hour forecast, or any forecast for that matter, to resolve an outflow boundary? Should you expect it to even be close? Yeah, it shouldn't even be in the analysis because it's below the resolution of the model grid anyway. And this boundary was put out by storms in the morning, so it was like near the time of the initial panel anyway. Looking at the local VAD wind profile from Amarillo in this case, and the observed storm motion, I get a storm inflow at 1,000 feet off the ground of about 35 knots, which is much stronger than this suggests. So in this case, you'd say, well, gee, mid-level storm relative flow looks good. That seems to be one thing that can discriminate between tornadic and non-tornadic storms. Is there any way I can enhance storm inflow on the mesoscale? And in that case, with this outflow boundary that's not drawn in here, the storms were developed and moved right along the boundary, which certainly would give you some indication that there's an enhanced tornado threat over what something like this would tell you. Okay, finally, just so you can get some numbers, what I did is I went back for all my 95 cases and did a quickie forecast test. I took every grid point where the supercells were observed, closest grid point, and I did a 12 and 24-hour forecast working backwards and said, what's the storm relative wind speed forecast at the surface layer and at 500 millibars for every case? If it was greater than 15 knots for both time periods at both levels at that grid point, then I considered it a hit. In other words, it was forecast to be tornadic, it was observed to be tornadic. And if any one of the, either say if 3 of the 4 were met, say the mid-level flow was forecast to be 20 knots both times and the inflow dropped below 15 knots on one forecast, it would drop out, and that's considered a forecast no. So that's fairly harsh judgment in my opinion of the potential to use the models, because what you're doing is you're removing your ability to interpret the model data. I'm just saying straight up, did it say at that grid point, according to this conceptual model, that it should or should not be tornadic? And it turns out I was able to get 86% of the cases, and there were about 55 or 60 cases in this forecast sample, were detected using that technique. If you look at least one of the forecast periods, especially the 12-hour right before, this POD goes up to about like 0.97. If you just look at 12-hour forecasts, at least one of them showed both parameters met. False alarm, there is some false alarm here, and you notice the overlap in the graphs. Again, it's maybe a necessary but not sufficient condition for multiple tornadoes or long-lived tornadoes. So there is some false alarm, but these combine to at least a reasonable critical success index of around 0.6. So what it does is it shows that, hey, maybe we can use the models, this coarse numerical model, to forecast supercell tornado environments and maybe pick out the non-tornadic ones. Okay, any questions on that stuff? If not, I want to just quickly show a couple of cases. How much time I have, Paul? Where'd he go?
About
5 minutes? Okay, I'll just show 1 or 2 cases here. This one's been in the news plenty. This is just had to work in some radar pictures somewhere in all this. This is the radar imagery from the Melbourne radar just, 2 weeks ago in central Florida with some of the damaging tornadoes. You see some evidence, something that looks like some sort of supercell structure, the tight reflectivity gradient on the southeast side, sort of a lima bean appearance. Of course, it becomes much more obvious when you put the storm relative velocities. In this case, the radar is down to the lower right, so we have 40 to 50 knot storm relative outbound velocities immediately adjacent to 30 to 40 inbound. So that's a very strong mesocyclone signature in the mid-levels, probably about 8 to 10,000 feet above the ground. And this was associated with some damaging tornadoes that, and here's just for reference some of the storms a little bit later, where we've got an additional storm. That other one's moved offshore. Here's another storm. I think this was the one responsible for the 14 fatalities somewhere near Kissimmee. And there's indeed another storm back here, had some rotation with it. And again, quite obvious mid-level mesocyclone signature with these. And there's also cyclonic shear with this storm down on the, further down this broken line. Okay, what did the sounding look like for this case? Here's, in this, unfortunately, the balloon launch for some reason didn't get in the system from Melbourne, so what I did was I run the risk of using a 3-hour forecast sounding as a substitute. And I figured, how bad can it be? Don't tell me, I know it could be screwed up to all ends. But anyway, you see a very strong vertical shear. There's turning in the low levels, a lot of speed shear through the depth of the profile. Surface-based parcels have moderate values of CAPE in the 1500 range. What does this look like, storm relative flow? Okay, what we've got here is the hodograph plot, and anyone not familiar with the hodograph, if you just put all the wind barbs at the origin and then plot the endpoints of the vectors, the hodograph traces that out. So these dots here are the assumed 1585 right moving supercell and a 3075. Turns out that's real close to the observed motion, so I use that point. And the important thing to note here is, you remember from the hodographs Al showed earlier, notice the storm motion is nowhere near the hodograph really. I mean, the closest point, so you see these shaded segments, those are every 3 kilometers. So 0 to 3, 3 to 6 kilometers, 6 to 9. So 500 millibars should be up here around 5 to 6 kilometers up in there. In this case, there's a fairly substantial difference between the storm motion and the hodograph. And if you straighten that out and take the magnitude, it's close to 30 knots. So that would fall right in the middle of the diagram. And indeed, these storms, there were multiple tornado-producing storms, each storm producing multiple tornadoes. So in this case, also you helicity arguments, most anything would have helped you this case. You had large helicity, large bulk Richardson shears, and large storm relative flow magnitudes. Now there's some other cases. We'll jump way back up in the continent. Here's one up by Minneapolis from some time back in, I believe, September of this past year. Again, radar's down to the south. Here's a cyclonic shear signature with the storm, fairly strong because this is about 100 nautical miles from the radar. And again, we look at the observed Minneapolis sounding down to the south of it. It shows what, not surprisingly, this loaded gun type profile, and again, winds veering and speed increasing with height. Sure enough, you put the observed storm motion was real close to the 3075 assumed motion in this case, which is nice, and the storm motion is well removed from the hodograph. And some of these things are like the vector layer averages of the storm relative wind speed and direction. So you see this storm was sensing low-level southeasterly inflow, denoted by this vector, whereas in the mid-levels, the storm relative winds are from the southwest at roughly 20 to 25 knots. These are 20-knot range rings. And then the high-level storm relative flows out of the west-northwest, roughly oriented to the direction of the storm motion down here. So that's the way I would interpret these. The failure modes are when these storm motions fall close to the hodograph there. So let me dig out the non-tornadic ones. I always hate to show these, but I got to do it. I hate non-tornadic storms. They shouldn't be allowed to exist, but... Okay, here's the sounding. This is one that I had the great fortune of chasing, I guess. Nice pictures from this day, but... Sounding from Stephenville, again, CAPE values consistent with severe storms, but notice there's the veering profile, but notice these winds are not particularly strong, and Al kind of hinted at this earlier. Winds drop off 15 knots, no more than 20 knots there in the mid-levels. That's always a warning sign. Anytime you see that speed decrease above the low-level jet signature, you get the idea that it might be some sort of looping hodograph, and in this case, the hodograph's kind of messy. The assumed storm motion in this case didn't work too well. It would have put it right on the hodograph almost at about 3 kilometers above ground level. What turns out, it was actually moving southeast. Still, this is the 3 to 6 kilometer mid-level layer. Notice that's pretty darn close to the storm motion. Now, another way we have of looking at this is the storm relative wind speed magnitude with height. 20 knots is the dash line. This is 10, 20, 30, 40 knots, and so forth. So there's plenty of storm inflow in the low levels, noted by this average here, 31 knots in the lowest 2 kilometers. But in the 4 to 6 kilometer layer, notice this average is down around 12 knots. And if you remember, convert that to meters per second, that's roughly 6 meters per second. And as it turns out, 500 millibars is about here. That length is about half of one of these range rings, which is about 10 knots, close enough. Where did that fall in the diagram? Were there any tornadic storms down with a storm relative mid-level wind speed of 10 knots? No, they were all like 15 knots or better, every single one in the database. And this is, of course, an independent set. This was not included in that sample. And it turns out the storm indeed was undercut by outflow. And that was confirmed by visual observations of some of us out there in the field. Long-lived rotating storm, large hail, damaging winds, no tornadoes.
Date?
That was April 18th of 92, Southwest Oklahoma. Okay, here's just another one, a quick example. This is a sounding again from Dodge City. Again, fairly moist profile. Cape values are consistent with severe everything else you typically see. Again, a veering profile, but what do we see again there? That weak winds in an absolute sense, somewhere in that 7 to 500 layer. But not quite as bad. Now notice the important thing is it's not just the speed, you have to look at the shape of the hodograph. Because it's not, you can't just say, oh, well, those winds are weak, well, therefore it's automatically going to collapse. You have to keep in mind which way is the storm going to be moving and how does that plot in a hodograph. And it's not, unless you do it all the time, it's hard to just eyeball looking at the vertical wind plot. In this case, the storm motion was a little more easterly, a little more to the right of the forecast motion. And the mid-level storm relative wind speed average in that layer, 16 knots. That's flirting with the tornadic cases. It turns out this one didn't produce any tornadoes. And you notice that there's a fairly deep layer where the storm relative winds are fairly marginal, like in the 15 to 20 knot range, all the way up to 7 kilometers. So if there was just a spike at one little part, I might be a little antsy to say that it's going to be a failure mode. But a relatively deep layer suggests that this storm will have ample opportunity to wrap a lot of rain around the backside of the mesocyclone. And in other words, produce a large hook echo and a lot of strong outflow. Should I about wrap it up? Paul, we running low on time here?
Yeah.
Okay, well, I would show the outbreak stuff, but we're just going to have to wrap it up. If you take anything from this half of the talk, it's first of all, I think we have some hope using larger scale data sets of discriminating between some of these tornadic and non-tornadic supercell environments using the mid-level storm relative winds. What seem to be necessary but not sufficient conditions for supercells in general is fairly strong storm inflow in the order of 15 to 20 knots. And remember, this is not near storm vortex type observations. This is background prior to storm forming, which fits with other observations of at least some values of storm relative helicity, at least some sort of values that we can detect in the 100 to 200 range. That's pretty typical. No big revelation there, but the mid-level storm relative flow seems to show some ability in this range of values to weed out the tornadic and the non-tornadic supercells, kind of separate the two a little bit more so that if you're faced with, say, warning decisions or something, you might say, hey, today is storm relative mid-level winds, everything else looks favorable for supercells. Is this a day I should consider tornado warnings for virtually any supercell that develops, or should I be maybe a little harder to impress and think maybe I better let this storm work pretty hard before I'm going to issue a warning, because chances are it may look good in the mid-levels, but what's going on down low may not be what you expect. Now again, I'm not going to say that that's going to solve all the problems of warning meteorologists face, because there hasn't been any attempt yet to apply this on a day-to-day basis to actual warning cases. I would just say, as a background first guess, you think, should my worst case scenario be a long-lived tornadic storm or not? And this can show some ability to help you make that decision. There's one that, according to the conceptual model, there may actually, if you recall the LP storm, the outflow challenge supercell, it suggests that there may be, at least hypothetically, some sort of upper bound to the storm relative winds. Well, on my graphs, you notice they stopped in values around 20 to 25 meters per second. But unfortunately, I can't find any cases above that. tornadic, non-tornadic, otherwise. I don't know if it's just a more general limitation that you can't get a supercell if the vertical shear is that strong, or what that's telling me. So that one is a little trickier. It may just also be to represent some sort of climatological limit to how strong the winds are in supercell environments. So there's not too comfortable making any strong conclusions there. Obviously, storm motion. If these storm motions are out to lunch, the 30-75, you have to know which way you're forecasting the storm to move. Then if you're staring at radar and it's moving 40 degrees to the right of that and some, 150% of the wind speed, obviously the storm relative winds are not going to look like what you think they look like. So you've got to check these versus observations. And of course, again, these POD and FAR with that simple forecast test suggests you can do a reasonable job. It's not perfect because that false alarm's higher than I'd like to see, and the POD's not 100%, but remember, this is using model stuff. You can modify any of these model forecasts with observations, and I'd encourage anyone that looks into this technique to do so. And then finally, this doesn't mean squat if you don't get a supercell in the first place. You can have the greatest looking storm relative wind forecast in the world, and at SPC we've fallen victim to that. Boy, this looks great, it's going to be outbreak the end of the world. And we missed the boat because there never was a supercell in the first place. So remember, you can't use this technique to forecast supercells. You have to use all the tools in your bag to figure out if there will be supercells, and if you need to be aware of low-level boundaries, any sort of large-scale support that may set up a favorable environment, look at different shear parameters, maybe even the modes of initiation of storms, but it's critically important to get supercells before storm relative wind speeds make any difference. So if anyone has any questions, I'll take them now. Otherwise, that's certainly all I've got for today.
Let's take one or two questions.
Okay. Yeah.
Rich, I was just curious, do you have October 26th of 1996 in your database there?
I stopped collecting data at the end of August of 96, so no.
I was just curious because that was the low top, very highly sheared case in central Minnesota where there was 13 tornadoes.
I did look at the storm relative winds because I was working that day. It was one, to be honest, I thought, well, this ought to be an interesting case to see if there is an upper bound, because I was getting estimates even with just a 1585 motion, assuming something wouldn't, since the Cape values were not particularly large and the vertical shear was extremely strong, I was guessing the storm wouldn't move that much slower and that much to the right of the mean wind. I was still getting storm relative mid-level wind speeds on the order of 40 to 45 knots, so we were pushing the 20 to 25 meter per second range, and those storms were extremely sheared, tilted over in the vertical, and they may have been flirting with too strong vertical winds, but I can't say anything conclusively about that. But I admit I was concerned. I thought this might be a case where it would be a failure mode because the winds were too strong. But obviously it didn't fail because there were multiple tornadoes. Anything else? Well, if that's it, I appreciate your attention and hopefully get something out of this.